Hello, my name is Tyler Smith, and this is my submission for the Zoom Spice recording assignment for 3020. Today I will be doing the common source amplifier circuit that was found in the design report. In the interest of time, I've already placed a few components. We'll place the NMOS transistor with the base and source tied. And we also will need a few other things like a power rail, positive 5 volts. And then we need to have two ground terminals, one for the input and one for the output. Then we'll start labeling some of these values. We'll do 50 kilo ohms for the resistor and 10 nanofarads for the capacitor. We also need to label some nodes for the analysis. We'll do an input node on this side and an output node on the capacitor side. And then now we need to be able to set the transconductance parameter of the MOSFET, and we're going to do that by setting, well, 3 values to transconductance and 1 value for the turn-on voltage. Right now we're setting the length and width of the gate of the MOSFET. Show both of those. And we also need to set up a model where we can set the KP value. The turn-on voltage of 0.5 volts and a KP value to 120 micro. On that set, I'm going to rename our MOSFET to match the model we created. Now, with this KP value and the width and length and the turn-on voltage and everything considered, the VDD and the R1 value, we should expect a bias voltage of about 0.591 volts. So we'll go ahead and set up our voltage source with the bias of 0.591. The sinusoid, we'll do an offset. So to maintain that small signal analysis, we'll set up the bias voltage, we'll do a small amplitude to not violate the small signal. And then we'll do a frequency of about 200 hertz because the minus 3 dB frequency and the bandwidth of the circuit with the capacitor and resistor is at about 380 hertz. So we'll go within that, the bandwidth. And we need to set up the simulation. We have DC sweep. We're going to be sweeping the V1 source from 0 to 5 with an increment of 1 millivolt, and this can be changed to increase or decrease the resolution of the analysis. The transient, we're going to do a stop time of 100 milliseconds just so we get a decent number of cycles at 200 hertz. And we want the step ceiling to be about 5,000 times smaller than the range, so we did about 20 microseconds. And then for the AC sweep, originally this was set to 0. We do not want it to be 0 because that is the DC condition. So we start at 10 hertz and we go to 10 gigahertz with 10 points per decade. Okay, that should set up our entire circuit here unless I missed anything. And now we can run. First, we'll run the DC sweep. We'll pull our V in and V out. And we can see that our turn-on voltage is about 0.5 volts. And we can grab a cursor here to get a better idea of where that middle bias point should be. We should expect 0.591 as stated earlier. So we'll go to the 2.5 volts. And we can see here it is about 0.591 volts, or 591 millivolts. Okay, and then for the AC sweep, that next, the V out, and we'll look at it as magnitude versus the frequency. And we can see here that low frequencies we get a gain of about 34 dB, and we should see a drop of a 3 dB at about 380 hertz. We see about 331, about 380 hertz, somewhere in there. And then finally, we'll look at the transient analysis. At 200 hertz, we should expect some pretty good gain, and then we should also see an inversion of the signal. So you can see here, our V in and our V out, pretty good gain. And we also see that it's inverted. The peak here is the valley here. And yeah, essentially that is this entire circuit and all the analysis parameters. Thank you.